Hello, everyone. Welcome to webinar A7, AM Smart, Advanced Manufacturing of Smart Material and Structures. This is the first webinar in 2025. Thank you for joining us, although it's late to say Happy New Year, but yeah, it is the first one, and I hope you started this year very well and doing well. So as you know, and probably seen the advertisement, the host of today is Professor Efrain Carreño-Morelli. Professor Efrain is from Switzerland. He himself has very nice research and background in additive manufacturing and also shape memory material, very much related to the topic of today. He has also invited some nice speaker. I leave it to him to invite to also talk about the speaker of today and also the topic of them. Fortunately, he's going to give also some information about the research they are doing in their group. Then we are going to listen to the presentation of the nice speaker of today. Thank you again for attention and following our webinars, and I hope you enjoy the webinar today. I hand over the webinar to Professor Efrain.
Yes. Thank you very much, Mershad, for this introduction. Then I welcome all the participants at this webinar. The speakers today it will be Professor Jose Maria San Juan Núñez from the University of Basque country in Bilbao, and the second speakers from the IMDEA Materials Institute in Madrid. Unfortunately, cannot participate because I received this morning the information he is ill, and really he was not able to come. He apologized for that. Then, because of that, because of this situation, I will introduce myself. I am Professor of Material Science and Technology at the University of Applied Science and Arts, Western Switzerland. Our activities are linked to everything which is related to the manufacturing of parts from powders by techniques as metal injection molding, press and sintering, hot compaction, and of course additive manufacturing. And I lead this group of powder technology since and advanced materials since 2011, and I am a co-organizer of the upcoming ASTM International Conference on Advanced Manufacturing to be held in Las Vegas this year. I am quite focused for this organization on the sinter-based manufacturing techniques as binder jetting and others. Then my lab is located in Sion. Then our strategy is related with providing solutions to industrial partners. This is why we are active in several materials, including the smart materials. We have state-of-the-art infrastructure for handling powders and mixing powders, to shape powders also by injection molding, by type casting, hot isostatic pressing, and we can sinter these powders in molybdenum furnaces, graphite furnaces, ceramic furnaces, etc. Then we do also the classical uniaxial compaction to make parts by press and then sintering. And we have state-of-the-art equipment to characterize powders and materials. Of course, microscopy, impurity analyzers, and we have all the necessary equipment to characterize powder particle size distribution and powder flow properties. Powder flow properties especially useful for additive manufacturing techniques. We have dilatometers, calorimeters, all that. And in additive manufacturing, since 2017, we have the selective laser melting or laser powder bed fusion possibility. We have desktop metal binder jetting 3D printer, which is a production machine with 1 liter of possible volume for build jobs. And we have our own technique. We called it solvent jetting on granules, which we developed many years ago. I can provide a description of that. Can be useful to make shape memory and superelastic materials because it offers a great flexibility on the base powders. This technique consists in making granules, like you see here. These granules are powder particles agglomerated with the binder, and these particles can be spherical or irregular, and one can include even sub-micron powders, nano powders, if one like. The idea is to make a spheroid-shaped granule, which is easy to spread in a layer, and then because you already have the binder between these particles, what is possible is just to drop a solvent. The solvent, which can be water-based, alcohol-based, any solvent compatible with the print head, can be used to soften the polymer into the granules and to paste the granules to each other. In this way, we grow layer by layer a green part, and after depowdering, we can debind and sinter. Here you can put pre-alloyed nickel titanium powders, and also you can put elementary nickel and titanium powder. And we have also tested mixtures of nickel and titanium hydride powders, spherical nickel and angular titanium hydride. With these ideas, we even made a patent application many years ago, and okay, it was at the origin of many others works. We have used this technique to process steel parts, soft ferromagnetic materials, and even hard metals as tungsten carbide, cobalt. I won't present details of the results, of the preliminary results on nickel titanium. Maybe it will be later. I will just shift to some results on selective laser melting. We start to work with that on 2019. We use this powder, titanium 50.8% atomic nickel. The powder came from rods we acquired, and we then we make how to say, we request atomization of this of the rods by partners, experts in the field. Then we obtained nice powder with good flow properties and purity, and we use it to feed our machine. We use a reduced working table, and the machine has the standard build plate of 125 millimeters inside, but this reduction is with 50 millimeters inside, okay, which allow us to use a few amount of powder. And then playing with the printing parameters and with the nickel evaporation, we managed to obtain parts with shape memory behavior and also with superelastic behavior. The shape memory behavior can be seen in these prototypes of stands. Then we managed to change the transformation temperatures to have a recovery of the shape after soaking in water at 50 degrees. For example, it was just the preliminary work, okay? And the geometry is quite similar to extent. Of course, the roughness condition is not proper, can be improved. And we also use a strut diameter of minimum of 200 micrometers, 0.2 millimeters. Okay. Then also we perform tensile test on dog bone shaped specimens. At the time, it was not common to perform tensile test. All the tests on the additive manufacturing of titanium nickel alloys was in mainly under compression because usually people are afraid about the cracks and the poor behavior, but we test in tensile conditions, and we obtained some nice results which can be improved after thermal treatment to show a superelastic plateau and fully recover of the part. Then the superelastic behavior of nickel titanium is important in applications as endodontic files. We have performed previously projects on metal injection molding of these parts, quite challenging projects. And these are just preliminary and preliminary prototypes to show that the limits of what can be performed. Then here are more details on the recovery of shapes of these stents. Okay, and more recently we have had the chance to participate in the project of the European Space Agency with my colleagues Gabriel Pachotti and Samuel Remerme. We built simple shape specimens, plates, and also some plates with a mesh into, and we sent it to the labs for validation. All the specimens need to be carefully controlled before putting it in the sample holder before be allowed to fly. This project is called Euromaterial Aging, and the goal is to test the materials under the harsh conditions in the space. Then this is a sample holder, and here there are specimens from several European labs, from 2 Swiss labs in particular, and we have some of these nickel titanium plates. There is one with shape memory properties, the other with superelastic properties, and after 1 year in the space, the specimens will be recovered, and we will test if the properties have changed. This is done near the Columbus module, and especially in the Bartolomeo hosting platform, which is outside of the International Space Station. The launch was last year in November, and we expect to recover the parts by the end of 2025. It can be a nice beginning for other applications in actuators, and even in the manufacturing in the future, why not, of instruments and even implants in long-term missions. Then thank you for your attention, and Okay, then if you have some questions, I can try to answer.
I see already. Thank you very much. I see already one question here in the chat. Maybe I can help to read it. It's written, how does shape memory effect work in a space? What is the actuation mechanism?
One of the goals of this project is effectively know how it can work, how it can change, because the radiation conditions and even the influence of atomic oxygen, which is in the space, can change the microstructures, can change the transformation temperatures, and probably the expected behavior in an actuator can be modified. We expect to know more about that in the future.
Thank you very much. Nice presentation, nice answer. Is there any other question? If you have, you can write it there in the chat. Okay, the other question is here. Do you need inert system to print NITI? How much oxygen level ppm request? It's from Chen.
Yes. Then when we use the solvent on granular 3D printing, we perform it until under air without any inert system in the printer. We take care in powder handling and also in strict debinding and sintering conditions, but the printing itself was under air. This is probably not the best, but with our prototype, we cannot do more than that. With devices like the desktop metal P1, one can work until under a protective atmosphere, and we do not have until now work with that. And with laser powder bed fusion, we have just used argon for commercial purity. And for the moment, these are our conditions.
Okay, there is another question. Actually, there are two more questions. Who ask you, especially for NITI alloy, how is your curing and debinding stage because of contamination, and how is your binder, or what is your binder percentage exactly?
Here in this, then for the moment we do not disclose too much about the composition of our granules. Hope it will come soon. But let's say that the debinding and sintering conditions are similar of powder injection molding.
Okay. And Efrain asks you, have you used and tested nitinol as well? If yes, could you please let us know if has it had any more advantage in comparison to conventional manufacture methods, for example, in medical usage?
Then, if I properly understand, yes, then for the moment, in our knowledge and capabilities, we are far from the standards, far from what is requested for medical applications. You know, the standards are quite strict. Many properties, including surface roughness, including fatigue, which is related to the surface roughness, for example. And the potential advantage, of course, is the freedom in shape, okay, in geometry, and also to save material. But the challenge are big in mechanical properties, in fatigue properties, in surface condition. And we cannot, we can list maybe some potential advantage, but this is just the very beginning of a nice adventure. We believe. Yes.
True. Maybe the last question from Islam. Thank you for presentation. Utilizing both binder jetting and LPBF for production of NITI, what would you say is the main challenge for binder jetting? Yeah.
Then for binder jetting is very nice for the mass production. It's much more how to say convenient than the laser powder bed fusion techniques, in our opinion. The challenge come mainly from the contamination because of the binder or the printing condition, and then the binding and sintering conditions. These are the main challenge. But it's a technique which offers reduced roughness compared with the laser-based techniques. Then, yes.
Okay, thank you very much. Yeah, I think we can wrap up this part. Thank you.
You're welcome.
Then I hand it over to you, Efrain, for the next exhibition.
Okay, then I stop sharing and I will let Professor San Juan to share.
Hello.
Share his screen. Yes, please, Jose Maria.
Thank you very much for your kind invitation. I would like to thank Professor Merrat for the organization of this wonderful webinar, and also my colleague Efrain Carreño-Morelli for inviting me to talk about this wonderful field. So let me. I have not prepared any presentation for myself. So. Just to say that I am a professor of physical metallurgy at the University of the Basque Country. I was working on powder metallurgy of semi-memory alloys from the 1995. And then I stopped during some time because I was working on semi-memory alloys at micro and nano scale since the 2006, in which I moved as invited professor to the MIT to work on semi-memory alloys at the nanoscale. And then when the additive manufacturing started to be developed, so we retake the powder metallurgy activities on semi-memory alloys, and my present talk deals with this topic. So let me perhaps share my presentation. I hope that you all are seeing my first slide.
Yes, very well.
Yes.
Okay, perfect. So I would like to talk about the microstructural and functional properties in copper, aluminum, nickel, semi-memory alloys processed by laser powder bed fusion techniques. This was carried out at the Department of Physics in the Faculty of Science and Technology at the University of the Basque Country, that is in the close to Bilbao, in the North Atlantic coast of Spain. So this project has been developed under the financial support of the Basque government in the frame of the El-Cartec Atlantic project that is being developed in collaboration with a couple of universities and several technological centers that all of them are involved in additive manufacturing on several materials. So in this project, we are the leaders on the same-memory activities for additive manufacturing. And in particular, these are my co-authors in this work. So what is the motivation for doing additive manufacturing on copper, aluminum, nickel alloys? Well, we have been working during several years in copper, aluminum, nickel single crystal because they offer exceptional superelastic and same-memory behavior as high-temperature same-memory alloys. For instance, I showed you here a couple of tests on superelastic tests on two different alloys at 190 degrees centigrade, in copper, aluminum, nickel single crystals. And this single crystal can be managed in order to have the transformation, all the transformation temperatures above, for instance, 160 degrees centigrade. So this means that they are working at high temperature between, and we can control the transformation temperature between 100 and 200 degrees centigrade, basically. So at present, these single crystals are currently used in space applications. And in fact, they are already flying in the space. At the beginning, we developed that in a European project. And then the single crystal produced in our laboratory are acting as trigger in the space actuator for releasing the solar panels or the release the satellites and so on. This is a technology that is tested, and at present we are doing the technological transfer to the companies of space application that produce space actuators. So, but the point is that for many applications, single crystal are not very convenient because single crystal has a limited shape for applications. And then we was thinking on polycrystals. But what's the problem in copper, aluminum, nickel? Polycrystal tend to be brittle. And this is a general properties in all copper aluminum based alloy like copper aluminum manganese, copper aluminum beryllium, and so on, because it's coming from the high elastic anisotropy of these alloys. So because of this elastic anisotropy, for instance, the elastic modulus in the 1-1-1 direction is 10 times higher than the elastic modulus in 001. So this is enormous elastic anisotropy make the concentration of stress at the grain boundaries, and the fracture in polycrystal is due to the stress concentration at the grain boundaries. To solve that, we can imagine that we decrease the grain size, and then we obtain, we minimize this effect, and we can manage with polycrystals with good thermomechanical properties. So this means that this is the idea why we use powder metallurgy of copper, aluminum, nickel, same memory alloys. And in particular now, with the development of additive manufacturing techniques, obviously we move to the production of these polycrystalline alloys by additive manufacturing. So this is the motivation. Then, for the production of additive manufacturing, we work in different aspects. As is a powder metallurgy technique, all the process begins by the atomization of the material. And then we explore 3 different lines. The first line is produce the massive material by laser powder bed fusion. In collaboration with our partners in the project, but we have also working on laser metal deposition with another partners, and also we produce the material by the classical metallurgy route by hot isostatic pressing and hot rolling in order to have a reference material, because this strongly textured rolled material is up to now perhaps the more performant material in this kind of polycrystalline alloys. So in the present talk, I will focus my attention in the first line, the production of this material by laser powder bed fusion, and but I will take as reference for the performance the classical route, the heap and rolling material, because this heap and rolling material exhibit really very good properties. And in order to compare it with the additive manufacturing produced components, we use exactly the same size of powder between 15 and 45 micrometers to produce this material, in order that starting point of the powders will be the same. So in this heap and hot rolled material by the classical route, we obtain really very good performances. So 4.5 superelastic behavior with a complete recovery, and a reproducible same memory effect that recovers perfectly up to 5%. So this will be our reference material to compare the progress on additive manufacturing when we obtain the material. So now the approach for additive manufacturing can be seen in this schema. So all start by the pre-alloyed powder atomization. Then we see the 15 to 45 micrometers powder, and then we use the laser powder bed fusion. And in order to optimize the procedure, we vary different parameters to get a good material. And then after that, we use a couple of steps, different steps for post-processing. Finally, when we get the optimal microstructure, we test the superelasticity and the same memory in different conditions, by tension, compression, bending in different conditions. And eventually we compare with the performance that I have showed you in the classical powder metallurgy route in order to verify the progress on the performances in additive manufacturing same memory alloy, in these same memory alloys. So as I commented, all start by the powder atomization that are doing by our partners of the SAID, that they have a small atomizer that produces 3 kilograms in its atomization. And then these are the kind of powders we get. So this is the complete distribution. And after sieving from 15 to 45, this is the distribution we have locally. You can see here a powder that as our transformation temperature is above temperature, you can see the martensites in the powder particle. And as I commented you, the atomizer produced 3 kilograms in each atomization. So in order to have enough material for the additive manufacturing process, we did 3 different atomization, but hopefully our colleagues from the SAID master very well the atomizer, and all the 3 atomization really match perfectly the concentration that was established as target. And obviously we get some ppms on oxygen and some ppm on carbon. But in general, the reproducibility of the chemistry of the each atomization is really very good. I have to comment here that in addition of copper, aluminum, nickel, as you can see the components, we add some boron and zirconium in order to have these elements as grain refiners to avoid further important recrystallization in the material. So the reproducibility of the atomization can be also seen if we perform a differential scaling calorimetry on the powders obtained in each atomization. So you can see here the comparison between these thermograms on the powders from atomization 1 and atomization 2, and really the thermograms are absolutely superimposed. So the reproducibility from one atomization to the other is quite perfect. So these are the powders we will use, and then we will produce the additive manufacturing by laser powder bed fusion using a Renisov 400 machine, and using also the reduced volume setup in order, because we, as I commented, we have not too much amount of powders. So we have done design of experiment changing several parameters like power of the laser, the hash distance, the scan rate, and the thickness of the layer. You can see here the different aspects. And then let me focus on the central part of this DOE. And sorry. This is the aspect we get by optical microscope. So when we have low power in this 5 or in this 9, here and here, so we have powders, we have pores very, very big, and this is improved in the case of 8, in which we have practically no pores. This is because for low powers, here and here, for instance, there is a lack of fusion. Okay, and you can get powder particles not melted in the cavities of the big pores that you find in your material. And the point is, even when the density of energy is high, because you can see here, with the same power, but because of different parameters, we can get here a much higher energy density than in this case, and in both cases, we obtain this problem. So this is an important point because it means that there is a critical threshold on laser power. If you have not enough power, you cannot guarantee the local melting of the alloy because of the high thermal conductivity of the copper-based alloy. On the contrary, for too high energy densities, like in the lower part, you can have K-hole porosity that even could prevent the building of the material, and really it become destroyed during growing. So this means that there is a narrow window between an equilibrium between laser power threshold and too much energy density. You can get in the middle. So in our case, the 350 watts and this scanner speed with these parameters give you energy about 120, and this was the best compromise to grow a clean material. However, in all cases, we obtain precipitates that appear during laser powder bed fusion. This problem was already indicated, published in a previous work, and is very important because it will destroy the functional properties of the same memory alloy. So there was some controversy on this point because some authors claim that it would be possible to get the functional properties of same memory alloys directly through laser powder fusion. But at least in copper, aluminum, nickel same memory alloy, it was demonstrated that this is not possible because of the precipitation of the equilibrium phase during laser powder bed fusion building process. To understand this aspect, let me show you the equilibrium and metastable phase diagram for this kind of alloy. So we start from the austenite at high temperature that has a phase that has an equilibrium stability domain at high temperature, and then we have to quench this phase to be frozen at close to room temperature, more or less, and then all Martensite transformation take place at lower temperatures. So if this phase, austenite, is cooling slowly, it will decompose in the equilibrium phases. But what is more important for us is this frozen beta phase is overheated. It will also decompose in the equilibrium phases because it's not an equilibrium phase at the room temperature in which, or 100 degrees centigrade, in which we are using as same memory alloys. So what happens when casting the material by a laser powder bed fusion? We can imagine that when we are building layer by layer our material, the heat of the melting pool is released on the material very fast because of the high thermal conductivity. But what is happening, in fact, is that when we scan the laser and we melt, and the melt pool is scanned along the surface, there is some overheating of several layers beneath the melting pool. And this is repeated again if we melt another layer above. Another overheating takes place below on the different layers. And this take place again and again and again when we are progressing in the growing, in the building of the material. So systematically, there is the scan of the melted pool over the surface produce an overheating of the previously built layers. And this is the reason why we are overheating the frozen phase and then produce a precipitation of the equilibrium phases. This is seen in our image of the scanning electron microscope, and we have done microanalysis, EDX, and line scan at the SEM, and these are the kind of precipitation you can find just after building the laser powder bed fusion sample. So in this case, these precipitates are copper-rich and poor in aluminum and correspond to the equilibrium alpha phase, this one or also this one. And on the contrary, this other equilibrium phase that I can put in green correspond to to a phase rich in aluminum and poor in copper. So this is the equilibrium gamma phase. So the not only the line scan, but we have also measured the concentration, the point by point of the different phases and the matrix, and then really we can identify that the precipitation observed correspond to the precipitation of the equilibrium phases during the laser powder bed fusion. As I commented, this is important because this will destroy the behavior of the material, and then we have to do a solid solution. Even if we do a slow quench at 100 degrees centigrade, we can get still precipitates. But if we quench at 0 degrees centigrade, and then we can do an aging to control the atomic order, we can get a fully transformed material in martensite and absolutely precipitated free. So we can say that the controversy is solved. Thermal treatments are required after laser powder bed fusion. This is also seen in the thermograms. If here you can see the differential scaling calorimetry thermograms of the as cast material that showed all the temperatures fully shifted to high temperature because of the precipitation, and after the thermal treatments, the material exhibit the very sharp transformation in the expected temperatures because of the concentration. So definitely thermal treatments are required, and this is no question. So then let me move to another post-processing activity. So here you can see the grow sample by laser powder bed fusion. This is the growing direction. This is the lower part. Okay, and then from this material, after the laser powder fusion, we perform hot isostatic pressing, and then the sample were cut for tension tests in a transversal direction, because we cannot get a big sample in the other direction, because of the reduced volume setup we are using and the amount of material we have. And then for compression tests, we have cut samples in the transversal direction and also in the building direction, in the direction of Z, in order to compare the thermomechanical properties. In what concerns the transformation behavior, I reproduce again the as cast material after thermal treatment, and the green curve correspond to the material after heap and thermal treatment. So we can say that hopefully hot isostatic pressing does not affect the thermal behavior of the material after laser powder bed fusion. Then let me move to the microstructure characterization. First, at room temperature, the material is in martensite. And then we have studied the martensite in both planes of the X set plane, so parallel to the building direction. And in the plane XY, this means perpendicular or transversal to the building direction. And I show you here the different martensite with different orientation. And in fact, these martensite are determined by electron backscatter diffraction and are identified by, in both cases, the self-accommodated groups of monoclinic beta prime 3 martensite on different orientation and with the relationship corresponding as the theoretical background. So we get a good martensite, and then we move to the characterization of the austenite. So to characterize the austenite, we have to heat up above the transformation temperature. So the austenite is studied at 100 degrees centigrade using the heating state and at the SEM with the EBSD. And then what we first observe is that there is this is the set direction of the welding process. So we have a columnar structure that is developed on the welding direction that exhibit a really strong texture on the 001 direction of the austenite. And this texture can be seen also in a vert view from the upper part of the material after drawing. This is a key axis because of the columnar grains are moving up to the surface. And then we can see also, we can confirm the texture of the columnar grains towards the upper part of the building direction. In the middle of these columnar grains, there are plenty of subgrain low angle misorientation boundaries. And so we can conclude that during laser powder fusion in these alloys, we obtain columnar grains with a strong 001 texture and a high density of long angle grain boundaries because of the rotation of these columnar grains with respect to the others. Okay. Then an interesting point is that this microstructure from laser powder fusion is not destroyed by hot isostatic pressing. In fact, these images are taken just after the heap on the laser powder fusion sample. So this means that the columnar microstructure and the texture is maintained after the hot isostatic pressing. Let me move then to the thermomechanical properties. So this is the superelastic effect in tension in the X direction, so transversal to the building direction. And this is a 100 degrees centigrade as a function of the different maximum strain. You can see that up to more than 2.7, we get a good recovery of the superelastic behavior. And this is the same effect at the different temperatures. What is interesting also is that we have done a cycling of up to 1.5 strain, and after some 20-50 cycles training, we get a complete reproducible superelastic cycle up to 1.5 strain, and all this is a 100 degrees centigrade. So this is very interesting aspect for a additive manufacturing produced sample, because this means that this could have the performance required, for instance, for many actuators in space. But we have also, remember that we have also used the material for compression, and then if we do compression of the sample cut in the Z direction, we get a good superelastic behavior for lower stresses and for highest strain. When compared with the previous results on the transversal direction, we can see clearly the difference. Pay attention that the levels of the stress and the strain are not the same for the Valls curves. And if we compare that, we can say that for the Z direction, so this means for the compression on the building direction, in the direction of the columnar grains, the stress are much lower than in the case of the compression of the transversal direction in red. And in the transversal direction, compression and tension are practically similar. So the difference is established between the transversal and the parallel direction to the building direction. This effect is also seen in martensite, because if we test this material at room temperature at 20 degrees centigrade, then the material is in martensite. So when we apply the compression in the parallel direction and in the transversal direction, we can get a much higher strain in this zeta axis. And as we are in martensite, there are some important residual strain that is recovered by heating because of the same memory effect. Okay, so we have this test correspond to the transversal, this sample cut in the transversal direction, and this blue correspond to the cut in the parallel to the building direction. So this means that there is a strong influence of texture because of the intrinsic anisotropy of the copper, aluminum, nickel semi-memory alloys. And this is because the 001 direction is the easier superelastic strain direction. And we have the chance that it corresponds to the laser powder bed fusion columnar texture on the building direction. So, and this texture will enhance the behavior of the material. So, if we move to the behavior of same memory, we have used one of the samples previously used during superelastic test. You can see it's the same shape with the head for the tensile axis. And but in order to visualize the same memory, we strain it in bending plus minus 4%, and then heat it, and so you can see the easy way in which the material recover the shape by shape memory effect. This has been made many cycles, and the material exhibit an excellent shape memory recovery during multiple cycles. So with that, let me move to the conclusions. So the processing parameters for laser powder fusion of copper, aluminum, nickel semi-memory alloys have been optimized. And the point is that a threshold on laser power is required, is recommended, and the density of energy must be limited to certain values in order to avoid keyholing. The post-processing step, two post-processing steps are recommended. Hot isostatic pressing reveals as a good method to decrease porosity, like in another technology of aeronautic. And in the case of laser powder bed fusion, thermal treatments must be applied to redissolve the precipitates after laser powder fusion or after HEP, both of them. And then these thermal treatments are required to redissolve the precipitates and functionalize the same memory alloys. The laser powder bed fusion develops a microstructure of columnar grains with a strong 001 texture that is good for the thermomechanical properties. This structure enhances the functional properties of copper, aluminum, and nickel semi-memory alloys. So just remember that an outstanding superelastic behavior about 2.7 recoverable strain has been obtained in both compression and tension in different axes, and anesthesia and good semi-memory recovery up to 4% has been obtained on cycling in the material produced by AMM. So if we compare with the classical route, we are approaching the performance of the reference material produced by powder metallurgy. We have not obtained yet the maximum result. Perhaps we are not yet ready for industrial production of these alloys through laser powder diffusion, but we are close to do it. So new progresses will be coming soon, and I would like to thank you for your kind attention.
I think you are mute, Efrain.
Can you hear
Now
me?
you are on mute. Yes.
Yes.
Okay, thank you very much, Jose Maria, for this nice presentation. It was really, really interesting. And we have time maybe for a couple of questions from the audience.
The time is up, but we can do a couple of questions, of course. I see one here is written, can we add some alloy element which can stabilize the beta phase and no precipitate of alpha and gamma will form due to overheating in LPBF?
Okay, thanks for the question. So we are from many years ago trying to add other element like not like refiner, but like quaternary and quinary alloys, and you can move a bit the domain of stability, but you cannot expand the domain of stability to room temperature. So the austenite will be always a metastable phase at room temperature, and so if you overheat the material, it will always precipitate. Okay. At present, we are not solving this problem. This is something intrinsic of this kind of material.
I can read the other question. You mentioned that copper, aluminum, nickel, polycrystalline tend to brittle and cracking. How do you deal with LPBF? Have you also tried it in LMD process, laser metal deposition?
Yes. So we have done a similar study. We are not finished the study yet on laser metal deposition. I have showed you in the presentation some samples we are already get, and we are finishing our results. But the performance will be probably more or less similar. However, the capabilities of the laser powder bed fusion are perhaps higher than laser metal deposition in order to produce, for instance, near net shape components. Okay, but I cannot the final answer, but probably the answer will be coming in some months. Okay. But we expect that from laser metal deposition, we will get also a good performance, because in a first approach, we have also seen that the laser metal deposition also generates some columnar grains during the growing process. And so the point is how to work the material in order that have the columnar grains in the good direction of your sample. Okay, I have not shown here, but we have also studied the fracture of the sample in test, and obviously, if you have the sample in the transversal direction, your columnar grains are here, and so you are applying tension in the lateral sides of the columnar grains, and this is not the good condition. So the ideal condition is that when you have the columnar grains in the direction in which you have to excitate in stress. Okay, for laser metal deposition, I think that will be a similar situation.
Yep. Maybe another question. Do you have a comment of martensite stabilization on alloy produced through LPBF?
I think that the problem of martensite stabilization is not coming strictly from the process. As I commented, after the process of laser powder bed fusion, you need to do the thermal treatments at high temperature. because if not, you will have precipitation, you will not have the right atomic order in your material, and in one word, you have not the right austenite phase to transfer to martensite. If you perform the thermal treatments, so you should try to avoid the stabilization of the martensite, and this is done by an aging at intermediate temperature, about 180 degrees centigrade, in order to stabilize the atomic order of the austenite, because you are coming from high temperature, and when you quench the austenite, the first action the atoms decide to do is to reorder in order to minimize the energy of the austenite. But during a fast quenching, this order cannot take place. So the order to the near neighbor take place, but the second order to the near neighbors is not able to take place. So you have to reorder that, because if you are not doing this reordering during the transformation temperature, during the transformation cycling, the martensite, when it's heated, will try to move to the austenite of the minimal energy. And if you have not the austenite of the minimal energy, you can lose the memory of your material. Okay? So to have a good behavior without no stabilization of the martensite, you should perform an aging treatment to guarantee the order of the austenite. But this has not practically no relationship with the laser powder bed fusion. It's, I will say, the same memory technology.
Thank you. If you don't mind, we leave it there, and I would recommend, if the audience would like to discuss more and ask questions, contact directly both Professor Juan and Professor Morelli.
With pleasure.
Professor Morelli, if you would like to end up.
Then I thank you, the audience, and also the speakers and organizer. And then let's meet at the next webinar 8. We will have in some short time. Thank you very much to everybody.
Thank you very much.
Thank you very much.